All right, Sandy, here we are at SES Battery in Woburn, Massachusetts.
Yep.
What are we going to do here?
Well, we're going to visit their factory, or at least their lab, and get a chance to see how they're doing their new lithium metal batteries. Yeah, so let's go and see what they've got.
We'll get into more details about the chemistry later. We started way back with coin cells at MIT, and back then they were developing this for high temperature applications. So in oil drilling, when you go down 2 miles down, and then you have to power the sensors.
Right.
So that was the initial application for high temperature lithium metal. And then
when was that?
This was 2010, 2011. We did a project with Weatherford and Halliburton, and then and also Baker Hughes. And then it's actually really interesting. They had this drill, and then so it's not the drilling. It's before you drill, you send the sensor down to collect.
The data on rock formation.
Right. And then those initially had high temperature primary batteries. And then what they want to do was, with high temperature, you go down, collect data, but then when the battery runs out, you can pull the whole thing up. So with a rechargeable, you could actually recharge it with the heat generated from the environment or the motion, basically recharge it downhole. That was a project we did with Weatherford and Halliburton. And then we started building these smaller cells. So this pack, this one has 6 inside. This actually goes inside the go-kart, and the format and the power capacity of that, we designed it so it's about 1865 cells. Yes. So the whole format will basically replace a device that will use 6 of the cylindrical cells. It's a pouch, obviously, but then the total capacity will match. And then we started doing more AI stuff. So we built these test boxes, and then we found a lot of the lithium metal, but also the high energy density batteries in general, lithium metal or silicon, it would swell a lot more, and then it's a lot more sensitive to the environment during testing compared to lower energy density lithium ion cells. So typically in normal lithium ion, you will care about just the electrochemical data, current and voltage during its use, maybe some temperature. But pressure is not so important to lithium ion, but super important for high energy density lithium batteries in general, silicon-based lithium ion or lithium metal. So we started adding this 4th parameter into the entire data collection, and then all the cells we build, doesn't matter if it's a small cell or a large cell, and then all the way from testing, from storage, we will actually monitor all the data. Electrochemical, thermal, these are standard for lithium ion, and then we introduce mechanical data. That's probably the biggest difference when it comes to application design between lithium metal and lithium ion. So if you put this inside a car or eVTOL, the mechanical data is a totally new aspect. And then 21, we built the world's first 100 amp hour lithium metal cell. This was actually built by our equipment vendor in Korea. This was the first. It's actually a real cell, and obviously we've improved a lot since then.
So are you building these cells here now?
Not here in Boston. We're building this in Korea and then Shanghai for the 3 OEMs. Honda. So Honda, we're building that in Shanghai. For GM, Hyundai, we're building that in Korea. We're building them and testing them over there. And so for A samples, but then for B sample, the plan is to build this maybe in Michigan for one of the OEMs. That's B sample. And then when we get to C sample, the plan is to definitely build a very large plant in the US for the 3 OEMs. But we started in high altitude HAPS application. So the solar powered, so
Yeah.
slow charge during
Yeah.
daytime and then slow discharge at night. Then we move to drones applications, slow charge but then super fast discharge, takeoff and landing.
Yeah.
And then we move to EV, land-based EV. And then now we are doing land-based EV and eVTOL at the same time.
Well, that's very impressive.
Yeah.
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 Especially if you
so-
can make it lighter. Yeah, it's cool.
Yeah. Shall we do a tour? So let's go inside.
Thank you.
Thank you. Yeah, sure. So here's where we do a lot of the new material synthesis. And then this area will feel like a lab, almost university or national lab, because really it is. And then a core competence, core part of our team are basically these senior scientists from national labs. And we do a lot of chemical synthesis.
So is that where you extract get your people?
Yeah, so for material team, we hire a lot from national labs. I think they're the really good. And then for the cell team, we hire mostly from lithium-ion companies, LG, SK, those places. Yeah. So then here we actually, a key material to enable lithium metal is actually the electrolyte.
Yes. So
Yeah.
that's usually the big chemistry secret.
Yeah. And then if you just try different formulations using existing molecules, solvents and salt, it's quite limited. So then we actually design new molecules that don't exist out there. And then now we design them, and then we also synthesize them here, and then we test them. And then we synthesize them here in small batches, about 100 kg, and then test them. If they work, then we scale them up. And then Louisiana in the US is actually a really good place for large-scale chemical synthesis.
Really?
Yeah.
What makes them?
Historically, there is a lot of oil companies in the Gulf of Mexico, Texas, and Louisiana.
Right, yeah.
And then there is a lot of HF capability in the area. And then if you want to make lithium salt or lithium solvent, a lot of the molecules using lithium battery, lithium ion or lithium metal electrolyte, they are fluorine based. So a lot of that capability, the upstream raw materials and the synthesis capability are already there. Huntsman, those guys are already there.
Cool.
Yeah.
Well, it's kind of interesting. What you're doing is what General Motors used to do. I don't know if you're aware of it, but there was this guy called Boss Kettering that Kettering University is named after now.
Yes.
And he was the guy that invented a refrigerant gas, fast drying paint, on and on and on.
Yeah.
Guy was genius with this kind of stuff. I don't think we see too much of it, except for Tesla. I don't see much being done in the area of creating new molecules and whatnot. It's
I think you almost have to because the existing molecules just you have that limitation, and then we use a combination of scientists designing new molecules. We do use some AI in some places, and then where the computation will help us basically help provide some guidance, some recommendation. A lot of those are junk, but then some are actually quite interesting.
Yeah. There's an old adage or something about scientist has 1,000 failures, and if he gets one right, he's in.
That's worth it.
Yeah.
That's what we do. Basically, we make mistakes, and then one thing that works, then
well, that's the thing. The only way I know of making stuff happen, especially if it's on the bleeding edge, is to figure out how to make mistakes.
Yeah, so here are the testers, and then we build cells in the back, dry room. We'll go in there later. And then basically we test them here. I want to show you something.
So what are these?
So these are, again, I mentioned pressure as a huge thing. So this is a R&D cell, small R&D cell, very thin. the large cell, the 100 amp hour that you saw has about 32 layers of cathode, 33 layers of anodes, so total 65.
Yeah.
This one is just 5 layers, very thin R&D. But then pressure, so for lithium ion you wouldn't do this, but then for lithium metal, pressure is hugely important. So we are testing different pressures, and then
So each one of those die springs is set to a different.
Yes. So we also have different pressures by using different springs, and these are earlier versions. We also have more sophisticated versions where we can actually dynamically modify the pressure. So these are fixed pressure, basically constant pressure the whole time.
Right.
But then we can actually modify the pressure during charge and discharge, connect that to the current, and then especially during discharge, that can actually improve the safety and the performance. So pressure is one thing we actually found to be quite interesting. These are more pressure
bigger
jigs.
ones, yeah.
But obviously, in the final device, it won't have these bulky pressures. In the final device, it'll be much lighter. And then I'll show you later the big pack that I'll show you later, and then that has the tape wrapped around it. So in R&D, we use these bulky pressure jigs to test different pressure. But once you have that value, then you can achieve that same value using much lighter materials.
Right.
Yeah. So this line is different from the Korea and the Shanghai lines because they are making the big and a lot of same product over time. But here is R&D, so we need to be very flexible in our material selections and in cell design changes. So this line is a lot of manual stuff, but it's at the same time has a lot of different material can be used. So it's really flexible, and that's really important too.
No, it's all right. This is good.
So for this line, this part is the more like R&D and analysis tools. So we have some like mechanical analysis, like a separator air permeabilities and FTIL 3D scanning and the sample preparations. So all the R&D stuffs in this area. And for this area is where we build the cells. And I don't know if you have seen it outside. We have many different types and sizes of cells can be built in here. Our process here, we are not making electrodes here. We are getting electrodes to processing it. So punching is the starting process, and then after we prepare the whole things, it's coming in here for the roll stacking.
So where do you make the electrodes at then?
In Korea.
In Korea.
Yeah.
We make the cathode.
Cathode in Korea.
Korea.
And this one I'm showing.
Yeah. Okay.
That's the shiny one is lithium, and the orange one is copper.
Huh. So is this a mechanical bonding, or how are you putting?
Yeah, just laminated.
Yeah, laminated.
Pressure together.
With a solvent or just?
No, just lithium.
press.
It's quite soft, so just
Yeah.
laminate on top.
Yeah.
Yeah.
Yeah, so this is very different from the other normal punching machines. It looks very similar, but actually the punching die design has to be designed for the lithium-metal, which is a very sticky material. So we have a real, different problem. When you prepare all the electrodes, so what Jeff is doing is stacking. So anode cathode will be punching out from here, put together. So that's what he's doing in there. We have three different stacking machines. So this one is one, and the other one And that's the big automatic one. So we normally using this tool at this time because it's a lot more flexible for any kind of design changes.
I'm surprised you're using air. I would have thought you were going to be using, a linear cylinder, a linear electric cylinder. Air's never been anybody's friend. I think air is good for breathing, but yeah, that might be something you want to look into if you're getting into, changing anything, because like I say, you can get a lot more control out of a linear cylinder, electric cylinder than
So we
air.
have multiple. That is the punching machines so we can using it too, and this one is hydraulic, so we can using it too, and this one is too. But it's also not the same for what our Korea team or Shanghai team is using for the big kind of anode cutting. So that's all the different concepts too. Yeah, we went through the multiple trials and the material selections, and we went through the a lot. And this is how we. So that one is already we have the electrode, lithium metal and the copper foil together. So this one I'm showing is like a kind of sorry.
So we actually want to start maybe on the left. This is pure lithium by itself. If you're on a room, can you touch it?
Yes, you can pick it up. So the lithium metal is really light and soft. Okay, so
This is the main difference between lithium metal and lithium ion. We use this as the anode.
Oh yeah.
it's nothing, right? So
Oh yeah, I can feel that. Like somebody just landed a butterfly or something. Yeah. So it's
Yeah.
very light.
Right. So the anode has a layer of copper substrate in between the two lithium foils. So you see here.
And then so the pure lithium, because it's so thin, it's hard to manufacture. So then for land EV applications, we put this on copper foil
Right. Yeah.
to give it more strength.
Yeah.
So it'll have your coppers.
Oh, I can actually feel that. Yeah.
And then Arun's going to show you for eVTOL and then aerospace applications, we don't put it on copper, we actually put it on titanium.
Right. So the copper is really heavy element, right? So most of the weight on the anode is just from the copper substrate.
Right.
So
Yeah.
to reduce the weight, you can first thing you can choose a different metal, and the second
Right.
thing you can do is perforate it. Like so, since this is just a current collector, right? So we could just take out most of the material and just give a skeleton.
That is really
Once you have
cool.
that, you could just laminate lithium on both sides of that.
Basically, I feel nothing.
Yeah.
So,
So obviously the cost goes up, but then that's for space
for
applications. so, yeah.
anything space or anything that
light.
flies.
Yeah, yeah.
Actually, I don't know what it is now, but it used to be $600 a pound, not a
Wow.
kilo, for the aircraft industry. If you could find some way to get rid of
Yeah,
a pound, they would allow you to spend $600.
Yeah.
So this is quite dramatic to go from the copper, which I could feel, to that, which,
Yeah.
like I say, a butterfly's wing or something. It's amazing. That's a really good idea. I don't think I know I haven't seen anybody doing that before. But then again, I haven't seen any battery specifically made for
Yeah.
for aerospace. So just out of curiosity, there's plenty of battery systems in aircraft already, and they go from the sublime to ridiculous. Have you moved into, say, swapping out the batteries that might be in the 787 or something like that? Because I can tell you right now,
Yeah.
I worked on that aircraft, and I can tell you for sure that if you can create something like
Yeah.
the bigger cells, of course, that would make a gigantic difference
Yeah.
in everything
Yeah.
that flies.
Yeah. Not for the 787 yet, because the large commercial, all the certifications take a long time.
Yeah.
We start with the drones, just almost simply because of easier certification process,
Yeah,
and then the
yeah.
smaller eVTOLs, 4-seaters.
Huh. Very good. I'm kind of, yeah, impressed.
So I call like some flexibility. This is kind of a multi-forming. We have a different size to kind of forming of the different depth based on the cell designs. So we can making the whole different things. So before we move to here, I have like 3 big boxes of that kind of punching dice, like which is very easier to modify.
Yeah.
So we can do that. Actually shows me like I can show you like how much of design changes we have went through, and
Yeah.
we're still like going through the chemical changes too, and then we get to this kind of different dice before we have that. There's a lot.
Wow.
We went through it. Yeah.
Very
So the
cool.
entire cell assembly process is very similar to lithium ion, and that's what we're trying to do. We're trying to make lithium metal by using lithium ion process.
Yeah.
So very similar, but lots of details have to be, like Xiong mentioned, have to be fine-tuned for lithium metal because of the foils is very different.
Yeah.
So backside of this line is all kind of a sealing and degassing type of processes. And so we are using the same machines from the lithium ion. But the punching, stacking, this part is a little bit different. Yeah.
So, where you use solvents? So, where do you do the? How do you do the wicking away? Is that your venting systems or something like that? How do you get rid of the outgassed stuff?
So we have a chemically just lines went through it. So this is the machine for the wetting and then degassing. So when you're using the chemicals, that's where we using the chemicals and we concerned about the fumes.
Yes.
So what we use is this kind of a chamber only.
So that's your fume chamber.
Yeah, so this is the chamber. I'm not giving this numbers here. So this chamber, when this chamber is working, and it's closing it, when it's open, it's connecting to the chemical just line there.
Yeah.
So it's a closing system, and then no fumes can actually escape. So it's gonna be the wetting. So wetting is we are making the vacuum breaking,
Yeah,
so making
right.
a better electrolyte.
Yeah.
Wetting, and this is the degassing machine. So we have from different size of the cells. So we have a different chambers, but it's gonna be the same thing. So we have the vacuum chamber and sealing. And this chamber, when it's operating, it also connecting the chemical with the line, so it releases the fumes.
And also for the solvent, one step that produces a lot of solvent is the electrode coating, which we do in Korea. And then that solvent, sometimes due to regulation, we actually recycle that. So we have a trap, and then we basically trap and then recycle the solvent.
Yeah, and that's what I was going to ask. Where does the tube go?
Yeah,
So
This one is
So you
very
gotta
small, so it's gonna be that filters and
Small
and
amount
this,
is
but
right.
as I said, the Korea line has a big coater.
Yeah,
And when you
yeah.
have a big coating, you need to dry out the solvent, and that part we gotta be collecting the solvent.
Good.
So that's different chemicals.
Well, I have to tell you, I've already said this, but it's worth repeating. That was a brilliant tour. Normally, I don't get a tour like that. It's usually a wide aisle tour and a lot of hand waving as you're moving. So I appreciate the fact that you went into the detail that you did. And I saw three things I've never seen before. The piercing of the titanium collector, if you like, or substrate. I never saw that before. And the density, like the weight differential between copper and titanium is just absolutely phenomenal. I think this is probably the best battery I've ever seen, period, when it comes to an aircraft kind of application. So I really did appreciate that. And I do appreciate all of the folks that basically helped us out here. So that's number one, I think, to start with. After that, I'd like to know a little bit more about when do you think you're going to be able to get into production, at least with the aircraft ones. That's the one that's in essence, I've seen lots of battery packs, but that really blows my mind. I'm really impressed with that.
Yes, I think for the drones application, the unmanned applications, I think that we can start large-scale production sooner, potentially as soon as next year, 2023. And then we have been testing these cells in some drones, smaller cells, and also the large 100 amp-hour cells in some drones. And then when it gets to the manned applications for land EVs as well as aerial EVs, eVTOLs, I think for land EVs, we expect 2026 for larger scale production. And then the eVTOLs, then the certification process might take longer, but around the same time as the land EVs.
Well, I will tell you, I'm going to put you in touch with John Romanelli, so he can talk to you or beg you for batteries, even if they're prototype. Of course, his vehicle is still prototype as well. So I think that it would be great if the two of you could talk. So we were talking before about a little of your background. I'm not sure how much of that actually got recorded, but I thought it was kind of interesting when you were talking about how you got started, and I think the audience would be kind of interested in knowing a little bit more about how you started with the process and of making batteries, and also the different projects you were involved in.
Yeah, so the whole thing started in 2007, and then back then it was the last term of the Bush administration and also the beginning of the Obama administration, and the Department of Energy gave a lot of funding to universities, including MIT, to sponsor batteries, solar cells, water purification, all these developments. So then I was part of that generation of students. I'm a physicist by training, but then a lot of us actually worked on batteries and fuel cells and solar cells. So that's how I got into this industry. And then this particular project, it started out as a solid-state lithium-metal battery. Solid-state lithium-metal, it only worked at high temperature. That was the main limitation back then. So the application and the project was actually funded by an oil service company based in Houston, Texas, for downhole drilling. So the goal was they usually use primary batteries, basically send this sensor about 1 mile to 2 miles down before the drilling starts, collect all the geological data, the sensors, and then trying to map a reservoir of the place. And then those used to be powered by primary batteries. And then anytime the battery runs out, you have to pull the whole thing up. It's a huge disruption to the operation. So if you could actually recharge the battery downhole while it's operating, by using the high temperature, the motion, the mechanical motion in the environment, then that would save a lot of the disruption. So that's how this got started. And then I started the company in 2012, and then we decided to apply this to drones, and then eventually land EV, and then eVTOL applications.
So 2012, you must have taken advantage of the tremendous amount of money that used to be laying around for investing in this kind of stuff.
Yes.
Do you still have those VCs or
yes.
whatnot? Or,
yes, the people that invest in us in the beginning are still with us.
Well, you said you had like about 150 people here, is that correct?
In Massachusetts, yes.
In Massachusetts. Yes. How many people would be in, like, say, Korea and Shanghai?
I think another 150, so total almost 300 worldwide.
And you were saying that you're going to be looking at another facility either in Michigan or Louisiana?
Yeah, so now we are in A sample, and then the A sample development is being done in Shanghai and Korea for the 3 OEMs. And then once we get to B sample and then C sample, the plan is to build both cell manufacturing plant and also material plants in the US. Cell manufacturing plant will be for the B samples and C samples, and then the material plant will be mainly for the lithium salt and electrolyte. The salt and electrolyte are two really key materials for this battery technology.
And where do they come from? I think I already know the answer, but it's like the Gulf Coast or something, right?
Yeah, so we're thinking a location along the Gulf of Mexico because that location has a lot of infrastructure from the oil industry, and then that infrastructure can provide access to HF and a lot of the fluorine-based chemistry that you need to make the salt and solvent.
Yeah. How much of that would you need? How many, I don't know, barrels or whatever, gallons? How many? What would you be looking at for the need for a factory that would have to produce, like say, a gigawatt of power?
Yeah, so roughly roughly 50,000 tons of electrolyte per year will give you roughly 10 to 20 gigawatt hours.
50,000 tons. It sounds like a lot, but really, it's
yeah,
like nothing.
It's actually highly automated. 50,000 tons, you're talking about 30 acres of land. It's not that big, and then less than 50 people. It's very automated.
So the guys from Louisiana and Michigan should be coming down here buying you big steaks and and flashing big checks in front of you. That'd be cool if you were up in Michigan. Like I say, at least a couple of the new I can talk about one. Like I say with John Romanelli's thing, but there are another couple of things that are going on in Michigan that would use those. Aircraft, at least, quality batteries. Yeah. So, are you going to be? So, I know that you've got GM, Hyundai, and Honda, right?
Yes.
Are you going to be producing the lightweight batteries for them, or are you going to be producing lithium metal, like using copper for them?
So, for land-based EV, for cost reasons, lithium will have a copper backing. So the land-based EVs that these 3 OEMs will be using will have lithium copper. Now for some of the flying cars, which these 3 OEMs are also working on, and then the defense applications, then we'll use a lighter backing, lighter current collector.
And you were saying that you think the one type of battery, you said 2023, but you said a year from now, so it must be 2024. Yeah, so do you think you're going to be able to hit target or put product into vehicles in 2024?
Land vehicles or drones?
Yeah, land vehicles.
Yeah, so for land vehicles, currently we are in A sample, and then this year, 23, we expect to get to B sample, and then 24, we can get to C sample. And then once you're in C sample, then the chemistry, the manufacturing process are almost frozen.
So how big a factory do you think you'd be looking at? I mean, battery plants go from the sublime to the ridiculous as far as sizes and what are concerned. How much do you think you're going to be looking to crank out?
Yeah, so I think for land-based EV, because it's still a new chemistry, we don't want to scale this up too fast, and then we do want to take this step by step and then make sure safety, everything is good. So for A sample and B sample, typically it's up to 1 gigawatt hour. Once you get to C, it's typically 10 giga. Obviously, that will depend on the actual needs, but we think a 10 giga for C sample will be a good starting point.
So a lot of people talk about vertical integration, and that usually means things like we're going to build our own seats or stamp our own parts or cast our own products. But one of the things that I'm always asking is, are you going to basically create your own automation, or are you going to buy it from somebody else?
Automation mean the process or the equipment?
The actual physical machines that are going to make the products. Because for me, I look at, I came from Ford Motor Company. I was in the machine tool world, and I saw how much or how quickly somebody's good idea became everybody's good idea.
Yeah.
But if you can control the actual machines that everything's built on, suddenly things are dramatically different.
Yeah.
So I'm just wondering
Yes.
which process you're going to be going to. Are you going to be using some of the Korean manufacturers for pouch style equipment, or how? What's your plan?
Yeah. So once before we got into A, it was just all R&D, and we focused a lot on materials. But now that we are getting to B sample and then larger scale manufacturing, one thing we realized a core competence for us is actually the system, this integration of the people that work on the line, the process, and the equipment. I mean, the equipment is just part of it. The equipment will be made by some other vendor, but then it'll be based on our design, our process, our people. So it's this seamless integration of the people, the process, and the equipment. I think that is going to be a really valuable core competence that we're trying to develop. And we are working really closely with some vendors, and then we've been working with them for a long time. So the equipment is not something you can buy off the shelf. It's highly customized to the process. And I think the line that eventually you will have, the team, the process, and the physical equipment, I don't think you can separate those.
Yeah, in my mind, that's the truth. But some other people would say everything's a commodity and whatnot. But actually, you guys are actually creating your own molecules for the solvent that you're using. Maybe you can dive into that a bit.
Yeah. So to make lithium-metal work, and lithium-metal is not a new concept. It's been around for 40 years.
Yeah.
It was actually there before lithium-ion. But then to truly make lithium metal cycle and safe, we need new material. And then one of the really key material to enable lithium metal is actually the electrolyte. And then in our case, we're using this high concentration solvent in salt approach. And then for the lithium salt, for the electrolyte, the solvents, actually, if you only try to formulate with existing materials out there, there is a lot of limitations. So then we hired this team, again, top scientists, software scientists, chemists, AI scientists, computation modeling scientists, trying to design new molecules. Not that we want to design new molecules, it's just these molecules that we want don't exist out there. So, and then based on experience, based on modeling, simulation, we do have a very deep understanding of the optimal structure that the molecules should have for cycle life, performance, safety. But then because these don't exist yet, then we actually design them and then we synthesize them here in small batches and then test them. And then once they work, I mean, most of them don't work, but the few that work, then we scale them up.
Are you looking at maybe trying to formulate something so you've got, in essence, a dry cell? So there's a very limited amount of solvent or no solvent. Are you looking at that as well?
It's not a top priority. So from a manufacturing perspective, the cathode, when we make them, we do try to reduce the solvent. So in the electrical manufacturing, we do try to make those using dry approach because the solvent is expensive, also causes a lot of recycling costs. But in the electrolyte, so in the cathode anode, the solvent is something eventually you have to dry up. But in the electrolyte, the solvent in the electrolyte, that will eventually stay in the electrolyte. It's not something that you have to dry up like you do for the solvents in the electrode. So then the solvent in the electrolyte, because it will stay there, then we make sure we design the solvent has good performance and also good safety.
You know, we were at the Tesla gigafactory in Austin, Texas. We got a tour just actually last week, and we got the opportunity to see what they were doing. And one of the things that they showed us, and I'm not sure whether we have that illustration, but the old process, which was basically a wet system, versus the new dry system. It's amazing how much smaller the footprint is, and how much money they're saving in wicking away the stuff that they really they needed for gluing things to, or used to.
Yeah.
Now I think it's all mechanical and a very limited amount of I don't know what you'd call it, but some sort of a solution. That to me looks like if somebody did that and I was exposed to it, I guarantee you I would be looking at how do I do that and save some money.
Yeah.
I think that it might be something now that Tesla has shown it to the world. It might be something you want to look at, because that's an amazing difference in
we are doing that.
Yeah.
Our CTO actually worked at Maxwell, and then he was part of the team that developed the dry electrical process. That process totally makes sense. The wet coating is basically you add solvents and you have this giant long line, then you have to dry the solvent. It's just stupid.
Yeah.
But the dry electrical process definitely makes a lot of sense.
Well, I'm kind of impressed by what I saw. I really think that, like I said, I've never been. Let me rephrase that. I'm more of a fan of a cylindrical versus prismatic, or sorry, not prismatic, but pouch.
Yeah.
And the reason is because all I got to do is have somebody bend it, and the next thing you know, I got an LG situation.
Yeah.
And that's cost GM, Hyundai, a tremendous amount of money.
Yeah.
So, but if what I saw today, I mean, your testing and validation stuff, your safety room, tells me that you've got that in mind, and you're trying to figure out how you can keep anything nasty from happening, because I mean, it takes forever to get credibility. But it only takes one hiccup and you're gone. You've really got a problem. So I'm just wondering how you're going to stay ahead of the game. I guess would be the best way to do it.
In terms of the form factor?
In terms of safety.
Safety. Yeah. So, I mean the pouch versus cylindrical versus prismatic. Of course, you have to sort of consider this from a holistic perspective. There's a energy density, packing density, all that. And then different chemistries, for example, different cathodes. If you use a high nickel with aluminum or without aluminum, sometimes that will change the chemistry. Some chemistries may be safer, but may tend to gas more, or some chemistries may be different. So if you consider all that, then certain chemistries that tend to gas more, then you will put them into a can that has a gas release valve, either cylindrical or prismatic. And then certain chemistries that are more stable and then can achieve higher energy density without the gas release, then you can put them in the pouch. I will say, I mean, the form factor is one thing that we and the OEMs constantly debate, and even the OEMs have not finalized yet.
That's right.
So, and then the cell that we're making, the 100 amp hour cell, that may not be the final cell. The final cell may be maybe 60 amp hours, maybe 70 amp hours. So for now, what we're doing in A sample and B sample is really to collect a lot of data, understand the boundaries of this chemistry. And we are developing lithium metal in cylindrical cells, in prismatic form factors, stack, but then instead of putting inside a pouch, we put it inside a hard case.
Yeah.
Yeah. So and then we are trying to see which format is the safest, and what capacity is the optimal between safety and performance. So I mean, this is why we have to build A samples and then B sample lines, so that you have a massive amount of cells coming off the line, and then you can make these decisions based on data. Otherwise, even the OEMs can't decide, is it a 46 amp hour cylindrical cell, or is it a 70 amp hour prismatic, or is it a 120 amp hour pouch? All these we have to collect data, build cells and collect data.
So if you had to make a prediction in the future, so let's talk 10 or 15 years down the road, do you think there's going to be some other chemistry or some other way to make a battery that gives, more power and maybe a little bit less costly?
So I think there are different chemistries optimized for different needs. If you want lower cost, then maybe sodium ion.
Yeah.
I think sodium is something that a lot of companies are working on for lower costs.
Right.
And the energy density is actually pretty decent. But then if you want higher energy density, I think lithium-metal, high nickel lithium-metal, especially for flying applications, eVTOLs. Now we are at 400 watts per kg. We can get to 450, and then with further optimization, maybe 470, 480 watts per kg. So I think for flying applications, definitely lithium-metal.
Yeah.
Potentially fuel cells down the road.
Fuel cells as in
Hydrogen fuel cells, yes.
Yeah. Maybe for big things like an airplane and whatnot.
Yes.
I don't see that ever happening. I think Toyota's kind of proved that don't work. And so I'm not as big a fan for automotive, but if it's heavy lift aircraft or
big
looking
truck.
at ships and things like that, big ships, that'd be probably a good idea for sure, if you could figure out. And that gets me to the last question I'm going to ask you is, where are we going to refine all this stuff? I mean, I know that everybody wants to have the clean environment and they want to go electric, but they don't want to mine and they don't want to refine, but we don't want to have it from another country.
Yes.
It's like this quandary that's sitting out there.
Yeah.
Do you think you're going to actually get all the materials that you want from North America, or have you made any arrangements with whoever?
We're working on it.
Yeah.
I think a combination of North America and South America plus Australia.
Yeah.
I mean, a lot of the lithium is in South America and Australia. And then refining currently, yes, some refining is done in North Carolina. But then I don't think there is enough. And there are companies, and then we are part of that, trying to build refining in North America. So instead of shipping lithium, spodumene, or brine to another country and then get refined and then processed, we can actually just refine in North America. And then that actually saves transportation costs. And
it's huge.
In the long term, actually may be economically beneficial.
Yeah, actually, on the northern border of the United States, between Canada and the United States, there's a huge area.
Yeah.
And it's loaded with lithium.
Yeah.
But there may be a lizard that will die. So we can't do much of anything there.
Yeah.
Do you think that the government will come in and start saying, well, sorry about that lizard, but we do have a need here?
Yeah, I think again, it'll be a holistic consideration. You're creating jobs. You're providing health benefit and all that to the local community, and then you are paying them, and then you're generating tax. So just a lizard dies, so that's okay.
Well, for the Native Americans, it'll be a big day because they own most of the property.
Yeah.
So it'll be better than even casinos. So.
Yeah.
Anyway, with that, I just noticed what time it is, and I know how much time we were supposed to have, so I'm going to basically, first off, thank you so much.
Thank you.
This was really
Thanks
worth my while. I really, really am happy about coming down to visit you guys. SES, I think, is going to have a very bright future. Really impressed. Anyway, with that, boys and girls, thank you so much for watching. Any final words?
I mean, I think it's been 40 years in the making, lithium metal. And then when lithium ion first came out in 1990, lithium ion didn't just come out as a new battery technology. It came out and then it enabled a new industry, consumer electronics. And I think for lithium metal battery, it'll be quite similar. And then it's not going to just come out as a new battery technology and then maybe just enhance driving range. I think when lithium metal comes out, it's going to enable a new industry. I think it'll be the flying car industry, eVTOL. So
cool. Yeah. Great way to end up. Anyway, thanks again for watching, and stay tuned for more. Thank you.